It's good to be here. I'm Mark Rober. This is science class. So, today, why is the sky blue? And maybe in your head you're like, oh, like blue light scatters. You just memorize that fact, but you should know by now, we're not about facts here. This is about mental models. Let's get a good mental model of why it's blue, because that's more useful. You can extrapolate and you just have a deeper level of understanding. So, as usual, we have a question, we have 3 clues. By the end of this, we should understand it better, and we use as few equations as possible. So, why am I doing this? Because, my review of the coronavirus is 0 out of 5 stars. This is kind of a bummer. You guys are home from school. It didn't really feel right to just not, do monthly videos. So I'm just trying to do something so we connect a little more, give you guys a little sense of normalcy in your life. Now, I have to start with something I'm very ashamed of. As you might know, my last video was about washing your hands and how you can transmit viruses by touching things. And most importantly, why you gotta wash your hands is we tend to touch our face. So you shouldn't touch your face. This is the exhaust port on the Death Star. Your eyes, your nose, your mouth. Having said that, well, let's just roll the tape. I'm not proud of this. Out of the gate, I'm not proud of this. And after sunk, what's gonna happen? Make it float. Can I make it float? Tell the person you're next to. That this beans, cucumber, mango, avocado, in regards to that density equation start to sink. So just a little bit. The gravity. You go, your ears, there's this, that's a verse, and it floats. I believe classes of, this isn't that easy. Yeah, so less than 27 is my goal today. You guys can keep me honest, all right? I'm really gonna do a better job. I picked this topic because, to be honest, I didn't have a good mental model of it. And so I basically give myself a day to learn something really deeply so then I can turn and explain it simply. You cannot explain something simply until you understand it well. So this, turns out, is a little bit more complex than last week, but I don't think it's too complex. I think you guys can get this, and we're going to make it happen today. The last thing I'll say is I could mess up here. This is live. We built this set. It's a miracle we're here right now. I won't get into it, but it's been a crazy morning. Things could come crashing down. If they do, we roll with it. I might misspeak and say something a little bit off. If I do, I decided I'm going to, in the video description, I'll put any corrections afterwards. But I appreciate your patience. I basically have a day to come up with these things, what the lesson plans are, and it's fast and loose and we're live. So, as an example, I forgot to state the assumption on the fart one that your intestines aren't under pressure. That's was one of the premises I wanted to state. That's the reason it makes you heavier. So things like that. Check back the video description in a few days, and if you're like, I don't think that was right, I'll try and tweak it. In general, you can trust me, but things just might be a little off because it's fast and loose. Okay, why is the sky blue? We'll just get right into it. Clue number 1. Electromagnetic waves. You're like, what's that? Electromagnetic waves are radio waves, Wi-Fi, your microwave, your cell phone that you talk on. These are electromagnetic waves. They're all around us, but we can't see most of them, right? So what's really cool and crazy about these, though, is the only difference between X-rays and microwaves and radio waves is the wavelength. So picture I have a slinky here. The more I stretch out this slinky, the greater the wavelength, right? If I count the little rings, the rings, they're less frequent. So it's a lower frequency, right? Lower pitch, like with sound. There's a lot of analogies here. If I stretch the slinky closer together, the rings happen more frequently, higher frequency, right? And the wavelength is smaller. So, what if I told you that there was a specialized instrument that you can use to actually sense electromagnetic waves, and it's within a foot of you right now? There's a specialized instrument for sensing electromagnetic waves. And maybe you're like, no, there's not. I'm on the couch. The TV's way over there. I'm not by anything electronic. It's not electronic. It's biological. And you have 2 of them. And they're in your head. It's your eyes. These are electromagnetic wave sensors. And you're like, what are you talking about? And I'm telling you, these eyes, You look around and it's like, bzz, that is 400 nanometers. It's telling you the wavelength. And you're like, bzz, that is 700 nanometers. And you're like, I don't get that feedback. And you do, as a lot of you probably know now, in colors. Colors are your brain's way of telling you different electromagnetic waves that are coming off things and hitting your eyes. So here's a chart that we'll come in on. And here's, big wavelengths, radio waves. These can be like as big as cities in their wavelength. That's a stretched out slinky, all the way to really, really tiny gamma rays, X-rays. Now there's this little narrow band here. The visible spectrum is what we call it, from about 700 to 400 nanometers. Red, orange, yellow, green, blue, purple. It's a rainbow. What's interesting about this is that if you go infrared, we can't see infrared, but some animals can, like snakes, right? Or mosquitoes or bed bugs. Now, why would blood-sucking insects, why is it helpful for them to see infrared? Well, if you've ever seen infrared, you could see body heat. So they find their victims, right? On this end of the spectrum, ultraviolet, like extraviolet, infrared, because red's over here, ultraviolet, you have like butterflies and elk. They can actually see this. They use it, or reindeer. They use it to navigate, bees as well. So our eyes see a specific range, but other animals can see more. Okay, so that's clue number one, electromagnetic waves. Just know that our eyes allow us to see a certain spectrum right here, and we see those as colors. All right, number two. Clue number two, the sun. Okay, so the sun's just like amazing. I give the sun a 5 out of 5 stars, unlike coronavirus. And the sun blasts this whole range of electromagnetic waves. It's not just a certain way. Everything at all times, it's like just blasting us all across the spectrum. It's like 1 trillion nuclear bombs a second is the energy coming from the sun. It's 93 million miles away, which means it takes 8 minutes and 20 seconds for the sun to reach us. So I am setting a timer for 8 minutes and 15 seconds because that means right now a photon just left the sun. It's on its way here. So in 8 minutes, we're all going to celebrate and be like, yo, welcome to Earth, photon. Like, welcome. What a journey you just made. 93 million miles away. It's on its way. We're going to come back to that in a second. That's going to be exciting. It's Naruto running its way right here, real fast, all right? So we're going to check in with that. The sun is all of the colors. So we see it as white, right? The sun kind of looks up, it looks white, basically. But that means, that's because when you combine all the colors, it's white. Now you may have seen this, I'll come over here, with a prism. Maybe you've seen like a chandelier in your room where it hits some glass and it splits it out. That's when it's giving you the clue that, it actually has all those colors in there. When you see that, it's kind of unpacking them for you. So the other thing to point out is the color you see is the color that's actually reflected. So it's saying that certain wavelength, red, is about 700 nanometers. That's the wavelength that's hitting my eyeball, not the color that's absorbed. If I see green, that's closer to 500. That's the wavelength of electromagnetic wave that's hitting my eyeball. So here's a question. If you have a plant, you love this plant. It's your favorite plant. You want it to live. I give you one choice of color to shine on it, day and night. What color do you choose? Remember, green, plants are green. If you chose green, your plant's dead. You killed your plant. That's really sad. I put an F in the comments, in the chat for your plant. It's dead. Why? Because remember, the color you see is what's reflected. So green is the one wavelength that plants don't need, right? They're sending that back. Any other color, it would get more nutrients and be able to do photosynthesis, but green is the one it doesn't need. So that's kind of a little helpful sort of mental model. So you should know also black absorbs all the colors. White reflects all the colors. This is why on a hot day, if you're wearing a t-shirt, a black shirt gets hotter than a white shirt because white's reflecting all the colors. Black is absorbing. You want further proof? I've got this flashlight here, right? So let's pretend this was a red flashlight. We have to use our coronavirus imaginations because I wasn't able to actually get a red flashlight in time. If I shine a red flashlight on this, what color is it? The paper's black. If I shine a green flashlight on this, what color does the paper become? It's black. It sucks all those colors in. It's like whatever you send at me, I'm sucking it in. I'm staying black. Now, let's take white. If I had a red flashlight, it was a dark room, and I shined it on this, what color does this paper look? It looks perfectly red. If I had a green flashlight and I shine on this, what color does this paper look? It looks perfectly green. So white is like, yo, I'm a color mirror. Whatever you throw at me, I'm just going to bounce back exactly what you send at me. So that's why when right now in this room, all the colors of the spectrum are hitting it. It's like, pff, I'll send them all back at you, baby. And it's going to look white because of that, because that's the color when you combine it together. So one thing that's kind of interesting to think of is a blue marker. Is it really like a blue marker? It's kind of like a blue blocking marker, right? I just put some liquid on this paper that's really good at blocking the blue electromagnetic wave. So it's like, I'm going to block these and send them back at your eyeball. So it's not really a blue marker. Oh, almost actually hit the camera. All right, so that brings us to clue number 3. The sky. Okay. What is the sky? When we say the sky, we're kind of talking about the atmosphere. What is the atmosphere? Here's the globe. There's like a layer around here that's like 80% nitrogen, 20% oxygen, right? And you might say, well, what would it look like if we didn't have an atmosphere? And there are exactly 12 humans who have a first-hand account, and only 12, of what it looks like with their own eyes to be on a planet or a celestial body with no atmosphere. You guess who that is? The astronauts who have walked on the moon. Because on the moon, you can see it's daylight there on the moon, but you could still see the stars at night, the sun's shining. It's just there's no atmosphere on the moon. The other benefit to that, you come back, is that with the atmosphere, it creates friction. So when asteroids come in, that's why the moon is so cratered. With our atmosphere, the asteroids come in, they get really hot, and they burn up, so they don't hit us. Usually, unless they're really big. R.I.P. the dinosaurs. All right, so that is the sky. Now let's talk about, things are about to get really crazy. So my favorite physics teacher, Paul Hewitt, gave an analogy. If we can, I'll bring this down. All right, here we go. Watch this. Okay, high tech on our set today. So you could kind of make an analogy of colors and the frequency in the electromagnetic spectrum to sound, right? See if we can see this. So something that has a higher frequency is going to sound, it's small, it's tiny, right? And purple and blue are at the end of the spectrum where they have a higher frequency. If something has a lower frequency, which is red, on the other end, which means a longer wavelength, lower frequency, less frequent, lower pitch, you would expect this to be really high or really low. I mean low compared to this, right? You hear the difference? So here's what's really cool. This is a cool mental model here. I'm getting this globe out of the way. The globe just broke. We've got Ken. We brought him back. Duct tape killed Ken. That's you on the surface of the earth. This is the sky, okay? Now what you notice here is most of the little pieces up here in the sky are shorter chimes, closer to this, because nitrogen and oxygen are really lightweight, right? Really lightweight, so they're going to resonate with something that has a much higher frequency. So here's the sun. When the sun shines, it sends all of these colors at the same time. Pretend this is above. It kind of goes off camera, so pretend I'm perfectly above. I send the sun all the colors. What happens is it's those little nitrogen and oxygen that are lightweight that kind of resonate with, of all the colors, they resonate most with the higher frequency ones, the blue and the violets, especially the violets, and they scatter that light. Because heavier molecules are less common. You see a long one here. It's like 10 times fewer heavier ones than the lightweight ones. Most of what gets scattered is the blue light. So that's why the sky is blue at noon when you're looking up. Oh, you hit this. It's because all the particles up there high in the sky are really lightweight, and they resonate with the higher frequencies. Okay? So that kind of helps with our mental model. But now that we do kind of have a mental model, the question is, what happens at sunset? So now Duct Tape Kilt Ken is over here at sunset, right? And the reason why that is, if I come to the board, this is the surface of the Earth, right? This is kind of the atmosphere here, this thin layer. Oh, welcome to Earth. There we go, there's the timer. It just came, it just arrived. So those little photons we talked about earlier, they're here. Look outside your window, welcome them. What a glorious moment. Okay, so the sun, right, at noon, it comes straight down. It doesn't have to go through much atmosphere. But at sunset, what happens when the sun's over here? I've already got it drawn here. Look how much atmosphere it has to come. You're over here. Duct Tape Kilt Ken is over here. It has to go through a lot more atmosphere. So now this is the situation. Here's Ken, okay? Kenny's up a little higher. Here's the sun. Sun does its thing. Wah! Sends all the frequencies coming. But what happens is that there's so many more little of these chimes coming that they run out of energy. At first it's like, whoa, they're shining real bright, really loud, the high-pitched. But by the time it gets over here, there's nothing left. So all the blue and the violet, all that's left are the lower frequencies, the reds and the oranges, right? It's the leftovers, basically, which is really interesting to think about. So when you're standing here at sunset, the reason that you see that as red and not blue anymore is you have to go through so many, and all of the higher frequency, there's no more energy left at those wavelengths. And so you're left, you get the leftovers of the longer ones. And now this mental model then helps us think about why, let's say, in Arizona, you get really beautiful blue skies, or right after it rains, the sky looks really deep blue. Well, there's no pollution, there's no, call it water moisture in the air. It's just those really lightweight little chimes. So it resonates really loudly at those, and it's very vibrant blue. If there's a fire, a lot of pollution, that's fine little particles in the air. And so the sunsets are especially beautiful because the blue light, dude, by the time it gets you, get out of town. Like there's no blue light left at all. It's all been totally scattered because there's so many little particles in the air, right? If there actually is a fire going on, you can almost look at the sun at noonday and it looks orange. The reason you can do that is because that blue light, and it's really dim, don't look at the sun by the way, but I'm just saying, those blue particles, they've been scattered, right? So, and then I'd say one more thing about this, you could expand this model even more. If you're in your bathroom and the window fogs up, right? What happens is you can't see, it becomes opaque. That's scattering all the light. Instead of it, because you have heavy particles, light particles, you got the whole range, right? So a cloud, or when it's foggy or hazy, those are like water droplets, and because you have all sorts of different sizes in there, not just a higher concentration of smaller ones, it's just scattering everything. And when you scatter everything, it's white. Okay? All right. So I'll end with this cool little experiment. This was a happy accident last night. We checked, it doesn't look as good on this camera as it did for me last night, but this is basically a sunset in a bottle. Up top, I'm going to show you now what I got at home, because it just shows up better than these cameras. But you can do this experiment yourself. All that's in here is just a little bit of milk. So that looks like the noonday sun, right? It's blue and white. Look at that. White sun, blue sky. When I move it down, there's just a little bit of milk in this beaker. You get a sunset. So what's happening there? Well, look at that. That's beautiful. Come back here, Alex. What you're seeing is that up here, the beaker is more narrow, so there's fewer particles to go through. As you go down and it expands out, there's more little particles for the blue to be scattered off, and all you're left with is the longer wavelengths, the reds and the oranges from my flashlight. How cool is that? You can do that yourself. Just a little bit of milk, maybe in different glasses. All right. So I think that's it. We kind of powered through that. Oh, the wireless knowledge of transfer from my brain. Hopefully some of the stuff came through. Like I said, this was a little bit more complicated, but hopefully some stuff made sense there and you have a better mental model of what's going on. So I want to show you guys some of the great video submissions I got last time with the neutral buoyancy thing. Before I do, I just want to say Bose saw what I was doing, and they said that they will give away about 8 of these 700s. These are like their dopest headphones they make. You know, they've worked with me before. I'm not getting paid for this, but they just said, hey, we'll give them away. So they're going to give 4 away to anyone who tells people about this class, either on Twitter or Instagram or Facebook or TikTok. TikTok? Is that the TikTok? We'll randomly pick someone who's telling people about this class so we can get more people here. 4 people get that, and then 4 people who accept the challenges or answer these questions and do a good job of it. You got to see some of these responses we got. Here we go.
The buoyancy in this is lighter than the force of gravity, so this is going to sink.
So Bose will be reaching out to you if you're one of the 8 people they selected. For this week's challenge, we'll come back over here. I love this quote, "Your shadow is confirmation that light has traveled nearly 93 million miles unobstructed, only to be deprived from reaching the ground in the final few feet, thanks to you." So with this in mind, the challenge this time for next Monday is to create some shadow art. Okay? This is where you find everyday objects around your house, and you kind of turn off all the other lights in the room, put a single point of light on it, and make something cool. Now, these are really advanced, so don't feel like you got to get this crazy, but get creative and maybe spell something out, see if you can make a shape, something cool that you wouldn't see it looking at the objects, but when you shine it from a certain angle, it looks awesome. So if you want to Google to get some inspiration, it's called shadow art. All right, so I'm going to end with a question, but first, this is my opportunity just to say something, and for me, the thing I want to talk about this time, real quickly, is this element of curiosity. The most important thing to say in science isn't, "Eureka, I have discovered this." It's, that's interesting. Like, what was that about, right? So last night, I had a moment like that with this beaker. I actually wanted a perfect cylinder, and then as I was like playing around with this and seeing where it would shine the best, I realized I could like actually create a sunset in real time. And I was like, that's interesting, and then I figured out what was going on. The microwave was discovered when someone was standing next to a radar and a friggin' Mr. Goodbar melted in this guy's pocket. And he's like, that's interesting, what's going on there? So then he observed that and did more investigation to figure out, oh, microwaves are a thing. I probably shouldn't be standing right here if I want children. So don't be afraid to be curious and to ask questions and to observe. The first step in the scientific method is observation, right? So that's how all great discoveries are made, by just observing. So pay attention to the world around you. Oh, I touched my face. And good things will happen. So let's talk. I'm going to show you the question for next time from my friend Sally.
Oh, hi, Mark. It's Dr. Sally LePage here, and I was wondering if you could help me answer a question I've been struggling with. How can you put your hand in water without it getting wet? Look, dripping.
Okay, so put your guess in the comments. We'll just do the comments below. And by the way, the answer isn't like wear a glove. What are some other creative ways you can keep your hand? By the way, Sally has a PhD in evolutionary biology from Oxford, and she's doing a live stream once a week. I'll put a link to her channel in the video description. She's starting from the basics and going up, so it's really interesting. All right, well, with that, that's it. What a hot mess this was, and I love it. This is beautiful. Class is officially dismissed, as you know. We're going to go to some questions, and then I'll answer these for like 3 minutes. And then you have your assignments, the challenge. I'll see you guys next Monday. Okay, so here we go. Did you consider other engineering paths? Because I enjoy electrical engineering, and I wanted to know what you think. You chose wrong. I mean, it's as simple as that. It's a fact. Mechanical engineering is the best. I'm just kidding. I don't, electrical engineering is like, and chemistry, you're like, I can't see those things, right? Mechanical engineering has always just really resonated with me. It's like, oh, there's this piece of chalk. I could tell you exactly how long till it hits the ground, right? I can see the things. I like the interactions, the collisions. So it's kind of whatever clicks for you. So for me, it's what clicked. But you should do what you like, even if you choose the wrong one. All right. What's the difference between normal people, or normal and colorblind people? So I should be careful on this because I don't want to go too far out of like what my expertise is. Colorblind people don't see the world as like black and white and like, oh, you get no information of electromagnetic waves. They just see it off a little bit and it's harder for them to distinguish. It has to do with like the cones in our eyes. So like certain colors are harder to tell the difference, but it's not that they see the world in like black and white. Why do shadows appear darker if it doesn't affect wavelength? All right, well, I have 2 more questions. I love the next one after this. Okay, I just got excited. Why do shadows appear darker? A shadow is just a lack of light, right? If you have a light in a dark room, so shadows are dark because there's no waves hitting that spot. If you turn off all the lights in a room, it's completely dark. That means there's no electromagnetic waves in that visible spectrum in that room, right? So a shadow is dark because it's just like an absence of electromagnetic waves hitting that spot. Last question, why is water blue from far away and transparent close up? Basically, why is water blue? And this one's cool because water actually absorbs, there's something about it where it absorbs infrared and wavelengths kind of more in this spectrum. So the reason water looks blue is because it's like sucking up and absorbing some of the energy that's like more red and infrared. And so what happens if all that goes away? All that's left to bounce back is the bluish greenish stuff. So there we go. That's the lesson for this week. Thanks for joining. We'll see you on Monday.